Alright, hello chat. I've returned to procrastinate and not work on the things I want to work on, but work on something equally as fun. We're gonna try and write malloc. Probably won't be done in one stream, but you know, could be pretty fun. Malloc, fundamentally, you just call it, you give it a size of how many bytes you want, and it returns a pointer to the first item of what it reserves that amount of bytes, tells the kernel to do that, and then it returns the first address so you can store in the pointer. But instead of using silly abstractions, I think it's time we write our own work, because are you even writing code if you're not reinventing the wheel? So we're gonna read about it. We're gonna hopefully do some work on it. That will be pretty fun. And we'll understand malloc at a more fundamental level? Yeah, type shit. Alright. Yeah, we know that. Compute memory as a library. The function when you're asking the librarian to reserve. Yep. Then it hands you a reference card. Yep. How does malloc work? Memory management segmentation. Memory can be visualized. Man, my Discord people are talking too much here. I'm gonna close it. There you go. Where was I? Oh yeah, memory management. So in the computer system, memory can be visualized. Array of bytes. Yep. For management purposes, this landscape is segmented into blocks. Let's open the paint here, so we can draw on it and yap. There you go. Okay, we've got an array of bytes. They're segmented into blocks, and each block holds data about size and whether it's in use or free. Okay, that makes sense. So we've got an array. We've basically got a long strip of memory. It's a big it's a big array of bytes, and then we chunk it. We arbitrarily tell, yeah, that a block is like 4 kilobytes or something. Linear search and allocation. When you call malloc, the function searches through these blocks, seeks out a free block that can satisfy the requested memory size. Okay, so let's say we've already got our block here. Don't know why I'm on pink, but fair enough. It's a nice color. So let's say we've got that, and we want malloc 2. And let's say these blocks are in use. Then it'll search until it hits this block, and then it goes, okay, these two are free. That makes sense. Seeks out a free block, requests vacant memory size, searches from the beginning, proceeding block by block, assessing the metadata. Okay, so in each block there's like data that tells you it's in use or not. Okay, pointer provision, post the allocation and optimal splitting. Malloc doesn't leave the program guessing where its reserved memory starts. Post after allocating. Did I miss this? Oh, if malloc locates a free block larger than the requested size, it doesn't hand over the entire block. The block is split on the requested size. Surplus memory remains free, primed for subsequent allocations. Huh. Oh, so let's say each block is like 8 kilobytes, but you only want like 4 bytes. No, let's say you want to store like 3 ints. That's like 12 bytes. Huh. Is a byte 8? Oh yeah, on 64. So it'll be 24 bytes. It doesn't make sense to hand over the whole block, so it'll probably chop it, and that would be 24, and that would be 8 minus 24. 8 kilobytes minus 24 bytes, yeah. Post the allocation optimal splitting. Malloc doesn't leave the program guessing. It's... Bro, my brain is not working. After you allocate and after you split the thing, malloc doesn't leave the program guessing where its reserve memory starts. It gives an address to the beginning of the memory block. Classic. Yep. So total length of block. Yep, fair enough. Memory management is not just about allocation. Yeah, you want to free it later. The process when a memory block called by alloc is no longer required, you give it back. Not doing so leads to a memory leak where, yep, and then you eat all of it and it crashes. Yep. Free identifies the memory block associated with the provided pointer, referencing metadata or bookkeeping information. Okay, so when you use malloc, you just free the pointer, but how do you know how many bytes? Because you're not passing that in. You're not passing. It could be just metadata or something like that. None of the significant changes of memory fragmentation. As memory is allocated and deallocated, you can. Yep. To address this, once a block is free, it checks its neighbors. If both of them are free, they get merged to a bigger block. Yeah, fair enough. Oh, so it's not just a. It's not like that. You have a continuous landscape. You go allocate, and then you deallocate. But then you want longer than that, so you allocate that and you deallocate that. And that keeps happening, and then whoop whoop, and then that guy goes, womp womp, my neighbors are free. Let's tear down the border. And now we are one unified chunk. That makes sense. Updating metadata. Yeah, yeah, yeah. That's pretty cool. You gonna teach me how to do it? Hello. Can I get some help? None. Getting to the. Yes, I would like to apply. Womp womp. Alright. System architecture. Project management. Chat. That's real chat. Oh, okay, well, I guess they're not gonna get. Yeah, fair enough. It's just a one-off thing. How how do you read block devices? Oh, well, just tell me how to use it. Oh. Yeah. This line calls malloc pointer int. Well, that's still nice, right? Let's keep that open. Oh, now I'm a tab hoarder. So how do I check? That's a lot of words. Alright, I like A bit more space to read that. Assuming they are S. Birkenberg. Oh man, Reddit fucking sucks. Alright, let's just copy this into a temp file then. There we go. Alright. Notification dismiss. There's Birkenberg. Is an implementation malloc free. There's a big problem. It doesn't deal with memory fragmentation. It actually leaks memory in that case. Small work less than exercise. There's also potential small problems with implementation. Unaligned pointers. Unaligned pointers. What does that mean? Okay. Break lines break the heap into 2 parts, allocate and free. Everything before the break line to the start of the buffer is considered allocated. So sleepy. Everything between the end of the heap buffer and the break line is free. What the sigma? You break the heap into 2 parts, allocated and free. Okay. Everything before the break line to the start of the buffer. Between the end of the heap buffer and the break. Actually, the break line starts off by pointing at the start of the heap, which means all memory is free. Oh, that's an abstraction. You have a function that just tells you what's free and what's not. Adjust the break line by number of bytes. Okay. What? Don't quell the man's knowledge. Oh, okay, well, fair enough. S break and M map. Alright, M map S break. Wow. Didn't even need to know what it is. Alright. S break. Dar. So break and S break are memory management system calls to control memory allocate to the data segment. Call from high level memory. Yeah. Break and S break are the only ways in which applications could acquire more space. Fair enough. Changing the space allocated dynamically. These calls dynamically change. Allocated, yeah. Changes made by resetting the program break of the process. S break is used to adjust the program break value by adding possibly adjust the program break value by adding a negative size while break is used to set the break's value. Yep. The nmap function has to map length bytes starting at an offset. Okay, what does break do? Break is used to change the space allocated for calling. Space is made by setting the process's break value to address space. Alright, I'll probably get off at like 11:30ish because I'm tired. Yep. Recognize rate resizes the heap process. Need to tell the kernel to adjust the location of the program break. Oh, so you have a heap. That makes sense. Oh, let's go back to here. So we have a stack. No, we have the heap. Silly little guy. And that's in use. And that's the break. Right? Yeah, that's the location from it. Since the memory that lies past the program break is unallocated. So that if we move the break up, we now get this much allocated. There are two functions associated with the process. Break sets the program break to the location specified by end data segment. Oh. So let's say you have break here. You move up, you do break 4, then it goes up by 4, and now break is there. Okay, S break increments the size of the program break by increment. So that's actually break 4 plus that length. But S break, you just take in 4 and it does the same. Fair enough. What does a return? What does S break and break? Okay, well, let's start writing some code. Whoa. Hello, my alloc. And looked include inst 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 the h u in unist ci triangle unistd the h. So int current break equals s break 0 printf, print out the pointer. Next line, current break, return 0, gcc main.c clear./a. That's the address of my heap memory. Nice. The previous break. Okay. Well, how do I examine? How do I examine the to see if they're in use? Oh, I don't need to. Oh. Okay. Rudimentary malloc is just s break. Okay, so let's write that. Void pointer my alloc int length return s break length int current equals my alloc. Let's say 4. Say 8. Current gss no sec fault. Ooh, it works. Wonderful. Oh, okay. So let's add 8. Oh yeah, it should be current delete. Let's do 16 and 4. Try that. GCC main./8. So I should have put in what? 8 bytes, 16 bytes, 4 bytes, right? So tired. 8, 16, 4. Oh man. Oh man. I just want to see the screen. This is hex. Can I do binary subtraction? Come on, buddy. What is that? Python read hex. Int minus int 0. They're not the same number. Oh. Oh, not on Vim. Try undoing the thing. Okay. Bits 2 bytes. Uh-huh. Oh, 16. 16. Uh-oh. 0. Yeah. So I did +4 +8 +60. Now I'm tired. I might just sleep. Yeah, but I want to write my own. I mean, that's cool. I would understand it better if I wasn't so tired. I think I'm gonna go to bed. The bed is calling.